In this lecture, we will be dealing with Industrial Robotics, Module 6, RoboCell Design and Control. In particular, we will be dealing with the topics on interlocks and error detection and recovery. Interlocks. An interlock in robotic work cell design is a method of preventing the work cycle sequence from continuing unless a certain condition or set of conditions are satisfied. It is a feature of work cell control which plays an important role in regulating the sequence in which the various elements of the cycle are carried out. Referring to examples 11.2 and 11.3 in the textbook, interlocks would be used for the following purposes. 1. To make sure that a raw work part was at the pickup location on the conveyor before the robot tried to grasp the part. 2. To determine when the machining cycle was completed before the robot attempts to load the part into the fixture. 3. To indicate that the part has been successfully loaded so that the automatic machining cycle can begin. In each of these instances, it is critical that one element of the cycle has been completed before any attempt is made to begin the next element. The method of regulating the sequence of the elements would involve the use of interlocks. Interlocks can be divided into two basic categories: output interlocks and input interlocks. An output interlock involves the use of a signal sent from the workstation controller to one of the machines or other devices in the work cell. For example, an output interlock would be used to signal the machining center in examples 11.2 and 11.3 to commence the automatic cycle. The output signal originates from the work cell controller and is contingent upon certain conditions being satisfied. In our example, the conditions would be that the work part has been properly loaded and the robo gripper has been removed to a safe distance. These conditions are usually determined by means of input interlocks. An input interlock makes use of a signal sent from one of the components in the cell to the workstation controller. It is employed to indicate that a certain condition or set of conditions have been met and that the programmed work cycle sequence can continue. As an illustration, an input interlock would be used in a machine loading application to signal the workstation controller that the part has been properly loaded into the fixture on the machine tool table. This condition might readily be sensed by means of a simple limit switch mounted on the fixture, which indicates that the part is in place. Interlocks are essential in nearly all robotic work cells, consisting of several operating pieces of equipment that must all work in a coordinated fashion. They serve to interface the various components of the workstation. Their use provides a synchronization and pacing of the activities in the cell, which could not be accomplished through timing alone in the work cycle. Interlocks allow for variations in the times taken for certain elements in the cycle. They prevent work elements from starting before they should start. They also help to prevent the damage of the various components of the cell. In the design of the work cell, consideration must be given not only to the regular sequence of events that will occur during normal operation of the cell, but also to the possible irregularities and malfunctions that might happen. In the regular cycle, the various sequential and simultaneous activities must be identified, together with the conditions that must be satisfied in order for each activity to successfully take place. For the potential malfunctions, the applications engineer must determine a method of identifying that the malfunction has occurred and what action must be taken to respond to the malfunction. Then, for both the regular and irregular events in the cycle, interlocks must be provided to accomplish the required sequence control and hazard monitoring that must occur during the work cycle. In some cases, the interlock signals can be generated by the electronic controllers for the machines and other devices used in the work cell. For example, numerically controlled machine tools would be capable of being interfaced to the work cell controller to signal completion of the automatic machining cycle. In other cases, the applications engineer must design the interlocks using sensors to generate the required signals. Interlocks are often implemented by means of limit switches and other simple devices that serve as sensors. In some cases, the RoboCell must make use of more advanced sensors in order to successfully perform the work cycle. Examples of the latter cases would include seam tracking in robotic arc welding, identification of part position and orientation on a moving conveyor, and determining that a component had been properly assembled before proceeding with further assembly work on the product. Now we will move on to the topic of error detection and recovery. Execution of the work cycle is expected to be repeated over and over for efficient operation of the RoboCell. However, malfunctions and errors can occur during the cycle, for which some form of correction is needed to restore the work cell to regular automatic operation. In most RoboCells, it is necessary to stop the work cell when errors occur and to provide human assistance for the corrective action. This generally results in production delays before the maintenance crew arrives to diagnose the problem and make repairs. There is a trend in programmable automation technology to attempt to endow the robo or other automated equipment with the capability to sense errors and malfunctions when they occur, and to take the necessary compensating action to restore the system to normal operation. This capability is referred to as error detection and recovery. Error detection and recovery consists of two ingredients: error detection and error recovery. The detection problem is concerned with the use of the appropriate sensors to determine when an error has occurred. It also includes the associated intelligence to interpret the sensor signals so that errors can be properly recognized and classified. Errors in manufacturing can be classified as random errors, systematic errors, and illegitimate errors. Random errors are those that result from stochastic phenomena and are usually characterized by their statistical nature. For example, part size in a machining operation would be expected to vary randomly about some mean value. Depending on the amount of the variation, this could cause problems in a subsequent manufacturing process. Systematic errors are not determined by chance but by some bias that exists in the process. For example, an incorrect setting in the production machine or fixture would likely result in a systematic error in the process. The third class is the illegitimate error, typically resulting from an outright mistake, either by the equipment or a human error. An error in the robo program would reflect this kind of mistake. Although this general classification of errors may be helpful in determining potential sources of malfunctions in a process, it is usually not sufficient to design an error detection and recovery system for a specific application. Please see example 11.5 in the textbook. It serves to illustrate how the errors might be classified into more specialized categories for a given process. Given that an error has occurred and that the error detection system has correctly sensed and classified the error, then certain corrective procedures can be initiated. The error recovery problem is concerned with defining and implementing the strategies that can be employed by the robo to correct or compensate for the malfunction that has occurred. The classification of errors is required during error detection because a specific recovery strategy must usually be developed to deal with each specific type of error. Recovery strategies can be grouped into the following general categories. 1. Adjustments at the end of the current cycle. This recovery strategy would represent a relatively low level of urgency. At the end of the current cycle, the robo program would branch to a subroutine to make the required corrections, then branch back to the main program. 2. Adjustments during current cycle. The error is sufficiently serious that corrective action must be taken during the current cycle of operation. However, it is not so urgent that the process must be stopped. The corrective action is typically accomplished by calling a special subroutine that has been designed to deal with the particular error. Three, stop process and invoke corrective algorithm. The error in this case requires that the process be stopped and that a subroutine be called to correct the error. At the end of the correction algorithm, the process can be resumed or restarted. For stop process, call for help. This action is usually taken either because the malfunction is one that cannot be corrected by the robo, or because an unclassified error is identified for which no corrective algorithm has been designed. In either case, human assistance is required to restore the system. Please see example 11.6 in the textbook. It continues from the previous example and show some specific recovery strategies that might be used for certain errors. The error detection and recovery system is implemented by means of the sensors used in the work cell together with the robo programming system. In terms of the programming requirements, the textual language have a distinct advantage in developing the sometimes complex logic that is often needed. For highly sophisticated robo cells, a majority of the programming may be required for the error detection and recovery system. The reference book used for this lecture is titled Industrial Robotics, Technology, Programming and Applications, authored by Mikkel P. Gruer, Michel Weiss, Roger Nagel, Nicholas Audrey and Ashish Datta. This is the second edition of this book, published by McGraw-Hill Publishers. Thank you.